Okay, here we have an intro to circuits. We're just going to get basic schematic images of what a circuit is going to look like, and very basic elements that make up a circuit, and define electric current, which is already up on the screen. Okay, so electric current is basically a rate of flow of charge. So if we can imagine like water flowing through pipes, that would be analogous to electric current through wires. We are going to deal with conventional current, which is the flow of positive charge. Positive charges don't flow. If we think about the atom, the electrons are on the outer edge of the atom, actually really far away from the center positive charges. The electrons are what can be easily transferred from one atom to another, or more easily ripped off of an atom. So in conductors, the electrons are kind of free to move between the atoms that make up the metal, so therefore they can flow through the wire. So conventional current is the opposite of that, and it's called conventional because it's a convention. So here's the definition of convention: a way in which something is usually done, especially within a particular area or an agreement between countries. So the way this is described all over the world in every textbook is the flow of positive charge. If we analyze it using positive charges or the flow of negative charges, we get the same results mathematically and conceptually. So it works. It's the explanation that works. Now we're going to look at a basic circuit. Basic circuits will consist of a battery, some wires, usually a switch, something that is going to use the electricity. This is a resistor. Okay. Now, in order for current to flow, and I'm going to switch on conventional current here, the circuit must be a closed circuit, which means that everything must be in contact. So you can see when I clicked on the switch closed, and now we're seeing the current flowing through the wire in terms of an arrow, right? So if I put on the electrons, it's showing particles, and again, it's moving the opposite way. Current really isn't like marbles flowing through a pipe. It's more like water and individual water molecules representing charges. And there can be molecules that are moving at different rates. It's just really that the net flow is in one direction. Okay, so if I wanted to open that switch, current stops. Now, we have the resistor and the battery in this circuit. If I wanted to make some measurements of some things, one of them being current, I can hook up what's called an ammeter to that circuit, and we can measure the amount of current that's flowing through that circuit. If I change a value of either the voltage or the resistance, we can change the value of the current. So the battery or voltage source is kind of like, using the analogy for water, it's like a pump that'll push it through the pipes, right? So if I increase the voltage, I'm basically increasing the power of the pump. So if I am increasing the voltage, I can pump more charge or move it faster throughout the circuit, right? If I change the resistance resists the motion. All right, you can see that the current goes down. And that is the basic relationship that we're going to look at, and it's called Ohm's law. So V is equal to I times R, where I is the current. R is the resistance. And V is the voltage. And again, this is called Ohm's law. A resistor is something that will resist the flow of current. They will use electrical energy and turn into heat. The variable for a resistor is, again, capital R. The unit is an ohm, which is a Greek letter omega. Okay, so this is the variable that ends up in the equation. This is the unit that ends up next to the value. Voltage is called electric potential, and it's proportional to electric potential energy. It's actually not the same thing, but we're not going to get too far into the differences between electric potential and electric potential energy. So if you hear me say electric potential or read that in a problem, it is talking about the voltage or the strength of the battery. And again, this acts like a pump for charge. The variable here is V, and then the unit is V for volts. Again, variable is in the equation, unit goes next to the value. If we go back to the circuit app here, we can see that we have elements in there that look like the actual things. Like that battery actually looks like a battery. But we won't draw circuits like this. We're going to draw them in schematic form. So if I change the form of the image here, let's see if it'll let me. There we go. Here you can see that it's using this symbol for where the battery was. Switch still looks like a switch. And then there is the symbol for the resistor. And if you look over here on the side, you can see that there's also a different symbol for the light bulb, and of course any straight line without any shape is going to be a wire. Here are the basic symbols that we're going to see. So here's the battery, which is a long line and a short line that are parallel to each other. The longer line is representing the positive side of the battery, and since we are going to talk about conventional current, which is the flow of positive charges, if I were to put a positive charge next to something that is positively charged, right, like charges will repel. So that means that positive charges are always going to flow in the direction away from that longer side of the battery. Okay, resistor is just a jagged line. Light bulb looks like a filament inside of a glass ball. Here's the switch. When we draw schematics, the ammeter symbol is just going to be a letter A, and it would actually have the lines coming off the sides too, just like the wire. So it'll connect to a wire like this, and same thing with the voltmeter over here. So ammeter measures current. I didn't define that unit yet, so let me do that here. So current is measured in amps. So the variable for current is I, which we saw in Ohm's law, but the unit is an amp, which is a capital A. The longer word is called an ampere. Okay, so variable, unit for current. All right, and then we'll just have a V in a circle for a voltmeter. So I just want to do one example problem with using this app here and Ohm's law. Alright, so if I close that switch, this circuit will be connected, but I want to write out some of my information here. So I know I'm going to want to use Ohm's law. And what I'm going to try to do is figure out what the current is going to be if I have a set voltage and a set resistance for the circuit. So if I click on the battery, if it clicks on the battery, alright, it took a little bit. So I got on the resistor first, so I have a 10 ohm resistor and a 9-volt battery. If I wanted to now solve the problem, I would just have to manipulate Ohm's law for I. Okay, and we would get 9 over 10, or 0.9. So if I close the switch, I get the current flowing, but I want to put the ammeter in there and actually check what we got. So let me cut that, move that out of the way. Let me throw the amp meter in there. Circuit's still closed, and we got 0.9. All right, so Ohm's law will work for any combination of those. What if we needed a certain amount of current? We can figure out how much voltage we have to supply across a certain resistance to get that current. Various combinations of this type of problem. However, with the simple circuit, it's nice because it's just Ohm's law. Of course, it gets a little bit more complicated when we add more resistors in different patterns throughout the circuit. So this is the end of the introduction to this. We're going to look a little bit more into multiple resistors being put into circuits in the next video.